Right, so this video I'm going to be talking about a concept in kinetics called half-life. Okay, so it's more than just a video game. And we're going to only consider usually first-order kinetics in this concept, but you can use it for any order if you use the integrated rate law and the fact that the concentration at any one time at the half-life is 1/2 of the original concentration. The main reason we consider only first-order kinetics is because it doesn't matter what the actual concentrations are in first-order kinetics. All that matters is the ratio is 1/2. For the other orders of reaction, it turns out that the half-life does depend on the initial concentration. So we do have to actually use the integrated rate law for that. So for first-order kinetics only, there's a special relationship for the half-life, which we'll call T subscript 1/2. It's the natural log of 2 divided by the rate constant K. Okay, so if you'll recall, the first-order rate constants are inverse time. Well, log of 2, which has no units, divided by inverse time will give you time. So if this is per year, then the half-life will be given in years. And of course, the 2 comes from this 1/2. So we're going to illustrate this with an example. So the example we're going to use is radioactive decay, which follows first-order kinetics. All right, so the example I'm going to use is based on radioactive decay of potassium, which is element 19. So the 19 tells how many protons, the superscript tells how many protons plus neutrons there are. And it decays to argon gas, which is element 18. Okay, so the total mass is 40 and 40. So the radioactive particle, which is produced, must have a mass of 0. So when we look at the masses of those subatomic particles, protons are very heavy, neutrons are very heavy and about the same mass. And then the electrons are very, very light, almost mass is 0. So this is going to be an electron of some sort. If we analyze it, it turns out that the subscript numbers also have to be conserved. So if this is 19 protons total, this is 18, there must be a positive charge. Sorry, this bottom line is the total charge, not necessarily the number of protons. Okay, so 19 plus is 18 plus, that means this is 1 plus. And so there's a special kind of electron called a positron that has a positive charge. And so the symbol for that, for the electron, this is called beta decay, so we're going to use the Greek letter beta for this. And the plus sign just indicates a positron because the charge down here is +1. So these numbers up here must add up to be the same on both sides. These must add up to be the same on both sides. That's how you figure out what the radioactive decay particle has to be. We'll talk more about that in nuclear chemistry. All right, so you can actually use radioactive decay to measure the age of some material if certain assumptions hold. And so, for example, potassium and argon can be analyzed in moon rocks. Okay, and the first thing we need to know is how long does it take for half of it to go away? And for this example, it's 1.25 billion years. All right, and so the problem is we take a moon rock and we analyze that the potassium ratio to the argon ratio is 1 to 7. Okay, and what does that mean? A ratio of 1 to 7? Well, if you remember your mathematics, that means as far as fractions goes, this is 1 part, this is 7 parts, total of 8 parts. So 1/8 of this to 7/8. Okay, so 1/8 of the original material a radioactive isotope is remaining. So 1/8 is actually a multiple of 1/2. So the way you get to 1/8 is you take potassium-40, some amount at times 0, and then half of it's left after 1.25 billion years. Geologists call them giga years. Then 1/4, then finally 1/8. Okay, so this moon rock is 3.75 times 10 to the 9th years old. Okay, so again, just to summarize, what you'd do is you'd actually set up the ratio of A over A naught. It's going to be 1/2 to the x power, where x is number of half-lives. And in this case, it was 3. So 3 half-lives is 3 times 1.25 billion years, or a total of 3.75 billion years.